so now we'll prove a second theorem where the proof is really close to the last one. So I want to do them back to back. They're not too long anyways. So here I'm going to start with a basis for V. And I'm going to assume that the basis is orthogonal. So we saw in last theorem that if you have a orthogonal set, then it's linearly independent. Now I'm assuming I have an orthogonal set that spans everything as well. So if it's orthogonal, then it's easy to find the coordinate vector of any element. So assume B is orthogonal and U is in V. So any element of V. So I know I can write U as a linear combination of these. And I know it's unique because I have a basis. Well, V's coefficient you could get pretty easily from using the inner product. So this will be U, I need more space, sorry. So the first one will be U inner product V1 divided by the length of V1 squared. This should remind you a bit about the projection, right? It looks like the projection we had in Rn. Same thing here. And same thing everywhere. So the inner product and the lengths give you the coordinates. And so in particular, if I look at U and the coordinate vector of U and B would be just these values here. So U dot Vn over length of Vn squared. And then if B is orthonormal, then it's even better, and you can tell it just follows from this, but let me spell it out. In that case, the length of the VI's are all 1, so they actually disappeared. I get U V1 plus U V2 plus U Vn, and then the coordinate vectors would be just the dot product with the basis elements. Alright, so the dot product gives you everything. Alright, so the second one follows from the first because the lengths are just 1, so I'm going to prove the first. So I know B is a basis. There are C1, Cn, so that U is C1 V1 plus Cn Vn. So I'm going to do the same thing we did with our zero linear combination last proof. I'm going to dot this with Vi. So if I dot it with Vi, I'm going to get U Vi U. That's going to be Vi dot A1 V1 AI Vi AN Vn. And then I'm going to split it. And let me take the constants out at the same time. A1 Vi V1 plus AI Vi Vi plus AN Vi Vn. And now, because it's orthogonal, all of the vectors in the basis are perpendicular, so all of these will disappear, and the only one that will stay will be the II one. Alright, so I get AI v the length of VI squared, just like I did last time, but this time I don't know that it's 0, it's actually equal to this. And so if I solve for AI like I did last time, so this is non-zero, since we have a basis, and so AI is VIU over length of VI.